Chesapeake Bay impact crater, where a cosmic bullet buried America's largest scar beneath a legendary bay. Scientists had puzzled over the Chesapeake Bay region's geological anomalies for decades before geologist David S. Powers remarked that the evidence pointed to something extraordinary buried beneath Virginia's waters. When his team announced their discovery in the 1990s, they revealed that the largest impact crater in the United States lay hidden just 300 to 500 meters beneath one of America's most iconic estuaries. The Chesapeake Bay impact crater stretches 85 kilometers in diameter beneath the mouth of Chesapeake Bay in southeastern Virginia, centered near Cape Charles at approximately 37 degrees, 16.5 minutes north, 76 degrees 0.7 minutes west. This buried impact structure, formed 35.5 million years ago during the Late Eocene epoch, represents one of the best preserved wet target impact craters on Earth and the sixth largest impact structure globally. The crater resulted from a bolide between 3 and 5 kilometers in diameter, striking the shallow continental shelf at approximately 17.8 kilometers per second, punching through 200 meters of ocean water and sediments into the granite basement rock below. What makes this crater extraordinary extends beyond its impressive dimensions. Unlike most impact structures that have been eroded, tectonically deformed, or deeply buried beyond study, the Chesapeake Bay crater remains remarkably accessible to scientific investigation. Its location on a passive continental margin means that no subsequent tectonic activity has disturbed the impact structure, preserving it in near-pristine condition for 35 million years. The crater contains 4,000 cubic kilometers of impact, breccia, a chaotic mixture of shattered rock and sediment that reaches 1.3 kilometers in thickness. This ancient cosmic collision continues to profoundly influence the lives of millions of people in southeastern Virginia today, affecting groundwater quality, land subsidence rates, river courses, and the region's vulnerability to sea level rise. The crater serves as both a window into Earth's violent cosmic history and a reminder that our planet remains perpetually exposed to hazards from space. 35 million years ago, Earth looked dramatically different from today. Sea levels stood unusually high during the Late Eocene epoch, pushing the Virginia coastline inland to near present-day Richmond, approximately 160 kilometers west of its current position. Tropical rainforests blanketed the slopes of the Appalachian Mountains, while a broad, lime-covered continental shelf extended eastward beneath the warm Atlantic Ocean. The water over this shelf reached depths of approximately 200 meters, where the impact would occur. On that fateful day, 35 million years ago, a bolide between 3 and 5 kilometers in diameter entered Earth's atmosphere, traveling at approximately 17.8 kilometers per second. Whether this object was an asteroid or comet remains uncertain, but its trajectory aimed directly at the shallow continental shelf off the eastern coast of North America. The bolide's arrival coincided with a period of multiple major impacts worldwide, including the Popigai crater in Russia, which formed at approximately 35.7 million years ago, and possibly the Toms Canyon impact crater, located 322 kilometers northeast, suggesting a potential cluster of impacts during this geological moment. The collision itself defied human comprehension in its violence and speed. The bolide completely vaporized upon impact, generating temperatures exceeding 2,200 degrees Celsius. The impact punched through the water column and sedimentary layers in milliseconds, fracturing the granite basement rock to depths of 8 kilometers. Within minutes, millions of tons of water, sediment, and shattered rock exploded into the atmosphere, with a plume of melted and ejected material rising between 24 and 48 kilometers high. The initial crater measured approximately 27 kilometers in diameter, but the sedimentary walls immediately began collapsing inward, progressively slumping and widening the structure first to 40 kilometers and eventually to the observed 85 kilometers. Chapter 3: The Eocene World Transformed. The impact occurred during a critical period in Earth's climate history, when the planet was transitioning from the greenhouse conditions of the early Eocene toward the cooler climate that would eventually lead to Antarctic glaciation. The Late Eocene epoch witnessed global temperatures significantly warmer than today, supporting tropical and subtropical ecosystems at latitudes that now experience temperate climates. Virginia's position along the eastern seaboard of North America placed it in a tropical zone, with the Appalachian region supporting dense rainforests rather than the deciduous forests present today. The continental shelf, where the impact occurred, represented a typical passive margin environment, characterized by thick accumulations of sedimentary rocks deposited over millions of years. These sediments included limestones, sandstones, and shales that had accumulated since the breakup of the supercontinent Pangaea, approximately 200 million years earlier. Beneath these sediments lay crystalline basement rocks of Precambrian and Paleozoic age, representing the ancient foundation of the North American continent. The shallow marine environment above the continental shelf teemed with life. Warm waters supported diverse communities of marine organisms, from microscopic plankton to large marine vertebrates. The seafloor hosted communities of bottom-dwelling organisms, while the water column above supported swimming and floating species. Coastal areas featured mangrove-like vegetation adapted to the interface between land and sea. This thriving ecosystem had no warning of the catastrophe approaching from space. The impact would occur during a time when several major cosmic collisions struck Earth within a geologically brief interval, suggesting either a cluster of independent impacts or possibly the breakup of a larger body whose fragments struck multiple locations. The Chesapeake Bay impact would prove to be one of the largest of these late Eocene events, creating consequences that would echo through geological time to the present day. The Chesapeake Bay impact crater's structure reveals the immense forces unleashed during the collision. The crater measures 85 kilometers in observed diameter, making it substantially larger than its initial post-impact diameter of 40 kilometers due to progressive slumping of unstable crater walls. The structure extends 1.3 kilometers deep and is now buried between 300 and 500 meters beneath the current surface of Chesapeake Bay and surrounding peninsulas. At the crater's center lies an inner basin measuring 35 to 40 kilometers in diameter, surrounded by a more complex outer region characterized by terraced walls and displaced blocks of sediment and basement rock. The crater's most distinctive feature is the exmal breccia, a chaotic deposit of impact, generated rubble that fills the crater to a thickness of 1.3 kilometers. This breccia represents a total volume of approximately 4,000 cubic kilometers of water, sandy rubble containing fragments ranging from microscopic particles to blocks measuring hundreds of meters across. The breccia consists of jumbled materials from all the rock layers, the impact excavated, mixed with shocked minerals, impact melt, and incorporated seawater. Remarkably, the breccia trapped ancient seawater between 145 million years old from the early Cretaceous period within the fractured rocks, preserving a sample of an ancient ocean. The impact completely disrupted the region's groundwater aquifer systems, truncating and excavating them. Today, the crater boundary acts as a hydrogeological barrier separating highly saline groundwater inside the crater, measuring 1.5 times saltier than normal seawater from fresher water outside, creating Virginia's inland saltwater wedge. Faults extend from the breccia toward the bay floor, posing ongoing risks for earthquake reactivation and potential saltwater contamination of freshwater supplies. The compaction of the breccia over 35 million years created differential subsidence, causing the land surface above the crater to remain lower than surrounding areas, which helped predetermine the location where Chesapeake Bay itself would eventually form approximately 10,000 years ago. Gauss 1 Sens. Chapter 5. Seconds of Apocalypse. The entire cratering event from initial impact to final breccia deposition lasted only hours to days. Yet those brief moments unleashed devastation across a vast region. The instant the bolide struck, it generated an enormous megatsunami that radiated outward in all directions. Recent research published in 2025 documented tsunami deposits 36 kilometers away in North Carolina's Sandhills region, providing the first physical evidence of the wave's reach. The tsunami possibly reached the Blue Ridge Mountains and may have affected areas as distant as Africa and Europe across the Atlantic Ocean. The kill zone extended several hundred kilometers in all directions from ground zero. Hurricane-force winds in the superheated atmosphere triggered massive firestorms across Virginia's Piedmont region, incinerating the tropical forests. Molten debris and ejecta scattered over approximately 10 million square kilometers, creating the North American tektite-strewn field that extends from Texas to Massachusetts to Barbados. These tektites, known as Georgiaites and Badiasites depending on their location, represent rock melted by the impact and ejected at such high velocities that the molten material solidified into glassy fragments while airborne. Impact debris has been found as far north as New Jersey, 274 kilometers from the crater. As the ejecta plume collapsed back to Earth, it deposited the massive breccia layer that now fills the crater. Marine sedimentation resumed almost immediately after the impact, rapidly burying the crater beneath layers of mud and sand. Over the following 35 million years, an additional 300 to 500 meters of sediment accumulated above the crater, hiding it completely from view. Yet the crater's influence never ceased. The York and James rivers make sharp turns to the northeast near the crater's outer rim, their courses deflected by differential subsidence. The crater continues affecting millions of residents through its influence on groundwater quality, land subsidence rates, and the region's heightened vulnerability to sea level rise. The immediate aftermath of the Chesapeake Bay impact transformed the landscape across thousands of kilometers. Within minutes of the collision, millions of tons of water, sediment, and shattered rock were ejected into the atmosphere, creating a plume that rose 24 to 48 kilometers high. The surrounding region suffered massive devastation, with a kill zone extending several hundred kilometers in all directions. Everything within this radius was obliterated by the initial blast, thermal radiation, and subsequent shockwaves. Hurricane-force winds in the superheated atmosphere triggered firestorms across Virginia's Piedmont region, igniting the tropical rainforests that covered the Appalachian slopes. Molten debris and ejecta were scattered over approximately 10 million square kilometers, creating the North American tektite-strewn field. These glassy fragments, formed from rock melted and hurled into the atmosphere, fell across a vast area extending from Texas to Massachusetts and south to Barbados. Debris reached as far north as New Jersey, 274 kilometers from the impact site. The impact generated an enormous megatsunami that radiated outward from the crater. This massive wall of water possibly reached the Blue Ridge Mountains and potentially affected areas as far as North Carolina, 38 kilometers away. Recent research published in 2020 tsunami deposits in North Carolina's Sandhills region, providing the first physical evidence of the impact's far-reaching effects. The tsunami may have crossed the Atlantic Ocean to strike Africa and Europe. Ancient seawater from the early Cretaceous period, 100 to 145 million years old, became trapped within the fractured rocks beneath the crater. The impact completely disrupted groundwater aquifers, truncating and excavating them in a pattern that would influence the region's hydrology for millions of years. Within hours to days, the crater filled with 1.3 kilometers of water, saturated sandy rubble known as the Exmoor breccia. Marine sediments then rapidly buried the entire structure as normal deposition resumed. Chapter 7: Discovery and Scientific Revelation. For decades, scientists puzzled over geological anomalies in the Chesapeake Bay region that defied conventional explanation. Unusual groundwater salinity patterns, unexplained river course diversions, and mysterious regional subsidence challenged geologists' understanding of the area. The breakthrough came in the early 1990s when USGS geologist David S. Powers, working with colleagues C. Wiley Poag and Bruce T. Scott, recognized that the scattered evidence pointed to a single, extraordinary cause: a massive buried impact crater. The discovery revolutionized understanding of the region's geology. Scientists had identified the source of the North American tektite-strewn field, mysterious glassy objects that had been found across the eastern United States for years without explanation. The crater's relatively shallow burial depth of 300 to 500 meters and its location on a passive continental margin made it exceptionally accessible for scientific study. Unlike many ancient craters, the Chesapeake structure had not been disturbed by subsequent tectonic activity, preserving its features remarkably well. The most ambitious investigation came with the 2005 to 2006 International Continental Scientific Drilling Program, a major international collaboration led by USGS geologist Gregory S. Gone. The project drilled multiple boreholes into the crater structure. The deepest borehole reached 1,766 meters below the surface, penetrating through the Exmoor breccia and into the fractured basement rock. Core samples revealed the crater's complex internal structure and provided unprecedented insights into wet target impact processes. Scientists discovered microorganisms living within the crater samples, suggesting the structure might provide habitats for microbial life. This finding has implications for astrobiology and the potential for life on Mars, where similar impact-generated environments might exist. Research continues to reveal new aspects of the impact. The 2025 discovery of tsunami deposits 36 kilometers away in North Carolina provided the first physical evidence of the megatsunami's reach, confirming theoretical models of the impact's devastating power. The discovery of the Chesapeake Bay impact crater in the 1990s fundamentally changed how scientists, planners, and residents understood the region's geological character. For the first time, decades of mysterious observations suddenly made sense within a single, coherent framework. The revelation had immediate practical implications for water resource management in southeastern Virginia, where millions of people depend on groundwater supplies. The crater boundary acts as a zone separating highly saline groundwater inside the structure from fresher water outside. Water trapped within the crater measures 1.5 times saltier than normal seawater, creating Virginia's unusual inland saltwater wedge. Understanding this pattern became crucial for managing the region's water supplies and preventing saltwater contamination of freshwater aquifers. Regional water supply planning now incorporates the crater's influence, guiding decisions about well placement and aquifer management. The discovery also transformed understanding of natural hazards in the Hampton Roads region, home to over 1.7 million people. Faults extending from the breccia toward the bay floor pose risks for earthquake reactivation, adding a new dimension to seismic hazard assessment. The crater contributes to the high rate of relative sea level rise in the Chesapeake Bay region, particularly affecting Hampton Roads, where subsidence compounds the effects of global sea level rise. Educational institutions and museums embrace the crater's story as a compelling example of Earth's dynamic history. The Cape Charles Museum developed exhibits explaining the impact structure, while informational signs at Cape Charles Beach helped visitors understand the hidden crater beneath their feet. The crater became an important educational resource for teaching about planetary science, geological processes, and natural hazards. The International Drilling Program brought global scientific attention to the region, establishing the Chesapeake Bay crater as one of the world's premier natural laboratories for impact research. Scientists from multiple countries collaborated on studying the core samples, generating dozens of research papers that advanced understanding of wet target impact processes. Chapter 9, 30. 5 million years of influence. The Chesapeake Bay impact crater's influence extends across geological time, profoundly shaping the region for 35 million years and continuing to affect it today. The compaction of the 1.3 kilometer thick breccia layer created differential subsidence, causing the land surface over the crater to remain lower than surrounding areas. This depression helped predetermine the eventual location of Chesapeake Bay itself, which formed only about 10,000 years ago when rising sea levels flooded river valleys at the end of the last ice age. The bay's position is no coincidence. It occupies the topographic low created by millions of years of crater-related subsidence. The crater's influence extends to the courses of major rivers in the region. The York and James rivers make sharp, unexplained turns to the northeast, near the crater's outer rim, their paths deflected by the differential subsidence of the underlying impact structure. What appeared to be random geological features are actually the surface expression of an ancient cosmic collision. The crater continues to affect groundwater systems throughout southeastern Virginia. The disrupted aquifers and trapped ancient seawater create ongoing challenges for water resource management. As coastal populations grow and demand for freshwater increases, understanding the crater's hydrogeological influence becomes increasingly critical. Faults within the breccia remain a concern for earthquake hazards and potential saltwater intrusion into freshwater supplies. The crater contributes significantly to relative sea level rise in the Hampton Roads area, one of the fastest sinking regions on the U.S. West Coast. While global sea level rise affects all coastal areas, the additional subsidence from the compacting crater breccia amplifies the problem locally. This combination threatens infrastructure, property, and communities around the bay. The discovery revealed that Earth's vulnerability to cosmic impacts is not merely theoretical or confined to the distant past. The Chesapeake Bay impact demonstrates that major impacts can occur on continental shelves in populated regions, with consequences that persist for millions of years. The crater stands as a permanent reminder of the planet's place in a dynamic solar system. The Chesapeake Bay impact crater remains an active area of scientific research, its legacy extending far beyond historical interest. As the largest confirmed impact structure in the United States and the sixth largest on Earth, it serves as a critical case study for understanding planetary processes. The crater's exceptional preservation and accessibility make it one of the world's premier natural laboratories for impact research. Scientists continue to study the crater to understand the effects of large impacts on continental shelf environments, a scenario that could occur again anywhere on Earth's extensive continental margins. The structure provides crucial insights into the formation and preservation of wet target craters, which differ significantly from impacts on dry land. research on the long-term geological and hydrological consequences of major impacts helps scientists predict how future impacts might affect human populations and infrastructure. The discovery of microorganisms living within the crater samples opened new avenues of astrobiological research. If life can thrive in the extreme conditions within impact breccia on Earth, similar environments on Mars or other planetary bodies might harbour microbial life. The crater thus contributes to humanity's search for life beyond Earth. The structure's ongoing influence on millions of residents in the Hampton Roads and Chesapeake Bay region ensures its continued relevance. As sea levels rise and coastal populations grow, understanding the crater's effects on groundwater quality, land subsidence, and seismic hazards becomes increasingly important for regional planning and public safety. Recent discoveries, including the 2025 documentation of tsunami deposits 386 kilometers away in North Carolina, demonstrate that the crater still has secrets to reveal. The Chesapeake Bay impact crater ultimately represents the intersection of cosmic catastrophe and human consequence. Buried beneath one of America's most important estuaries, invisible to those who live above it, the crater nonetheless shapes daily life for millions of people. It stands as a profound reminder that Earth's history is written not only by gradual geological processes, but also by sudden, violent events from space, whose effects echo across millions of years.